Hi, everybody. We are back. In this segment, we are going to do a little bit of work in R to verify that pseudo-inverse one-step learning approach to finding the linear regression estimated parameters by solving that OLS problem. And again, this was that one-step learning approach where we had that analytical solution. We could take that pseudo-inverse matrix, multiply it by our output vector, and boom, we were able to recover all of those parameter estimates in just one step. Before we get too deep in the example here, I just wanted to draw your attention to a few preloaded data sets in R. There is the data sets library, as well as the mass library that I'm going to load up here just to kind of show you a lot of data that's already built into R itself. And if you run this data function with the open close parentheses here, you can see here it says these are all the data sets in the package data sets. And there's lots of things here: monthly airline passengers, carbon dioxide uptake, chicken weights, lots and lots of stuff. And if you scroll down, you can see here is the mass data set. And there's, again, lots and lots and lots of preloaded data options inside the mass data set. And what we are going to do today is we're going to utilize the MT cars data set, which is a pretty small data set from Motor Trend magazine, on different types of models of vehicles, the different characteristics of those vehicles. And we're going to go ahead and think about building a regression model using this particular preloaded data set today. So if we go ahead and run the view function, we can get just an idea of what the data set looks like here. So it looks like we have miles per gallon data, number of cylinders, displacement, horsepowers, D ratio, weight, the number of seconds in a quarter mile, number of gears, whether or not it is a manual or automatic transmission, which is one thing that we may be of interest today, carburetors, etc. And again, if you need to know anything about a particular data set you've loaded, you can always do question mark, the name of the data set. And when you run that line of code, you'll notice in the console window here, it pops up with a description of exactly what these variables mean, the number of the units of measurement, et cetera, as well as the source. So we've loaded up this MT cars data set, and we want to do a little bit of descriptive analysis to understand the structure of that data set so we could see it here in the spreadsheet form. It says showing 1 to 10 of 32 entries. So we know we got 32 observations. There are 11 columns total, which means we have 11 variables in the data set. And if we run the dim function on MT cars and we look down in our console window here, we should be able to see here that we recover that same information. There are 32 rows and 11 columns in that particular data frame. And we're going to go ahead and look at a pairs plot for the first 4 variables in the MT cars data set here. So what we want to do, first 4 is MPG, cylinder, displacement, and horsepower, gross horsepower. And we want to basically pull just those columns. So I have a little bit of an error here in this code chunk. I want a comma saying we're going to take all the rows, nothing before that comma, but I want columns 1 through 4, variables 1 through 4. And we're going to go ahead and run that pairs plot just so we can get a preliminary idea of the types of relationships that we see in our data here down in this bottom right panel. And we notice a few things. Looks like in this plot here, which has miles per gallon on the horizontal axis, displacement on the vertical axis, that we got what looks like a strong negative relationship here, is downward sloping relationship. Same with miles per gallon and horsepower. So we have some idea here about some relationships in our data. There's what looks maybe to be a weak positive relationship between displacement and horsepower here. Also in this diagram. So there's a little bit of exploratory analysis to be done. And what we are going to do momentarily is build a regression model based off of some observations in this data. And the approach we're going to take today is we're going to start out kind of manually filling out the pseudo-inverse approach. So we're going to construct the X matrix. We're going to construct our Y vector. And then we're going to use some matrix functions in R in order to manipulate those in order to compute our pseudo-inverse solution. So the first thing we need to recall here is that anytime we're constructing that X matrix, okay, our matrix of input data, if we are including an intercept in our regression, and this is important, if we're not doing a regression through the origin, if we're including an intercept, then remember the first column of that X matrix has to be a column of ones, and that's going to correspond to our beta 0 estimator. So I'm going to create this variable here called vector of ones, and I'm going to use the repetition function here. And what this says is I want to repeat the value 1, and the number of times I'm going to repeat that is equal to the dimensionality of MT cars, but just the first element here in brackets, which are the number of rows. So I'm saying create a column of ones that has the same number of rows as MT cars, which is equal to the number of observations. So what this does here is it's going to generate a vector that has dimensionality n by 1. It's going to have, again, n rows, the number of rows of that MT cars data, and it has the number 1 repeated that number of times, just one column. So I'm going to go ahead and run that. And then we're going to use the class function to check the object to see what type of object in R this is. And we can see it is a numeric object. We actually don't want a numeric object here. We want a matrix object in R. So what we're going to do here in the next line is we're going to convert that vector of ones into a matrix object using the as.matrix function. And then we're going to do the same thing for columns 2 through 11 in the MT cars data set. So remember what columns 2 through 11 were. Okay, that's cylinder all the way out to the right to carburetor. And note that does not include miles per gallon. We are not going to include miles per gallon in the X matrix because that is going to be the Y variable that we're going to predict. We're going to see, can we build a model to predict the miles per gallon of a vehicle based on all these other 11 individual characteristics, or how many we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, based on these other 10 characteristics here. Now, the other thing we're going to do here is I'm using this SIbind function, and what that SIbind function does, it's going to take this column vector of ones, and it's going to stack it next to this matrix, which again is going to be this as.matrix MT cars. We have 10 columns here. And then we also have this column of ones to the left. So the SIbind function, what that does is it creates the X matrix by adding a column of ones. Okay, and that column of ones is there specifically to pick up an intercept term. If we did not have that column of ones, if I ignored line 17 and I didn't have this value here, we would be missing that column of ones and we would just be running regression through the origin. Okay, with no intercept term. So let's go ahead and create the X matrix. And we got a little bit of warnings here, but no errors. So I think we're in good shape. And let's go ahead and just view what that X matrix looks like so we can see it. So here is V1, our variable in column 1, which you'll notice is just that, that vector of ones. Okay, and then we have our other 10 variables stored to the right. So this whole thing we're looking at here is the X matrix. And you can check the class of X actually and see that it is a matrix object. So we can use matrix manipulation now. We can take the inverse of X, we can transpose it, et cetera. The other thing I wanted to recall here is just a little bit about some subsetting. So if I wanted to look at the first element of the X matrix, let's say, so let's go ahead and substitute X here. The first element, 1, 1, first row, first column, we know is just the number 1 here. Okay, so when I pull that first row, first column entry, okay, that does show me the first entry in that particular object, that matrix object X. If we had switched it back to MT cars, okay, then I would be pulling the 1, 1 element, the first row, first column element of MT cars, which is the miles per gallon for our first observation, which is the Mazda RX-4, which was 21. And when we run that, we do see we get that value retrieved in the console window here. Again, if we leave that first row entry blank, that says pull all the rows, but in line 26, we're just going to pull the first column. So the first column of data in the MT-CARS data set. That is the entire set of 32 MPG entries. So if we were to run that, okay, you'll see what are we getting here. We're getting those 32 mile per gallon entries. Okay, and if we wanted the first row of data, then we're going to leave the column entry blank. We'll just say, hey, I want the first row, but all of the column entries, since we left the column entry blank. And if I run that, we're going to pull basically the first observation entirely, which corresponds to that, again, Mazda RX-4 here. And these are all 11 variables associated with that Mazda RX-4. Now, the next thing we're going to do is we're going to construct the Y vector. Okay? And the Y vector, again, we're going to create a matrix object here. It is a vector. It's a type of matrix object. And we're going to do that by pulling only the first column from MT-CARS, and hopefully you remember what that is. If we look back at our MT-CARS spreadsheet, we know the first column corresponds to that MPG variable. And again, that is the regressant. That is the variable we are trying to predict in our model. So we're going to go ahead and run that. And you should note again in your global environment in the top right corner, and I know my video might be covering a little bit of that up here, but these elements that we're generating are showing up there, and we can check the view of what we just created, this matrix Y, which is really a an n by 1 vector here of these miles per gallons. And you'll notice I didn't create a column name for it. I'm not going to worry about that too much here, but it's pretty easy if you wanted to edit the column names in R. A quick internet search will show you how to do that, or Stack Overflow. It's fairly simple. So what we're going to do next, now that we've created our Y vector, we have our X matrix, is we're in a position to go ahead and compute the pseudo-inverse solution. And just a few notes here. R uses a solve function to compute an inverse matrix. So I know we talked about the inverse was looked like it raised to the -1 power, but we're going to use the solve function here to compute an inverse. And this T function in R is used to take the transpose of a matrix. And anytime we want to multiply two matrix objects in R, we're going to use this expression, percent sign, multiplication sign, percent sign. So percent star percent, we use that to multiply two matrix objects together. And we're going to use all three of these functions, solve, transpose, and multiplication, in order to calculate our pseudo-inverse matrix. So here is the pseudo-inverse matrix. Okay, you'll notice what that looks like. So inside here, we have the transpose of X multiplied by X. So that's X transpose X on the inside. And then we're taking the solve of it, which means we're taking the inverse of that X transpose X matrix. And then we're multiplying that result by the transpose of X. So this entire thing here is our pseudo-inverse matrix. All right, so we can go ahead and construct that, and then we can check the dimensionality of it. And it does have 11 rows, okay, and it's got 32 columns. So it is, again, of dimension k plus 1 by n. We have 10 regressors, right, plus that intercept term on the right-hand side. So that's where these 11 rows are coming from, and the 32 columns correspond to the number of observations. So in order to recover our optimal beta parameters, we're going to go ahead and take that pseudo-inverse matrix and multiply it by the Y vector, using, again, this matrix multiplication in R in line 39 here. And when we run that line, okay, what we've now generated is we've generated the beta vector, the optimal values of the beta vector that solve the OLS problem, ordinary least squares problem, that cost minimization calculus problem, which we looked at in a fair amount of detail in a previous video segment. And if we go ahead and run line number 40 here, we're able to compute or look at our results of our work. And you'll notice when we do that down in the console window here, okay, what are we getting? Well, we're getting a vector here of how many elements. Well, if we wanted to check how many elements, we could run that dim function, but we can just look here, I think, and count. We got this first term, which is the intercept term. And then we have our coefficient, our beta 1 on cylinders, our beta 2 on displacement, beta 3 on horsepower, beta 4 on drag ratio, beta 5 on weight, so on and so forth. So this is our vector of betas. That represents the solution to that ordinary least squares problem, and we've recovered them using this one-step learning pseudo-inverse approach here. Just to make sure we are getting reasonable results. Okay, we got 11 betas estimated, including beta 0, that intercept term. Let's go ahead and verify now that the results that we generated using the pseudo-inverse method are the same as the results we would get if we use the built-in LM function, that linear model function in R. And what we're doing here again is we're saying, I want you to build a linear regression model where the Y variable is MPG, that is what we're trying to predict. And on the right-hand side, right, we use the little tilde, like our equals sign, to separate the left from the right-hand side of the equation. But on the right-hand side, we have a little dot. And what that dot says is it's telling R to use all the other variables in the data set as regressors or control variables on the right-hand side. And then we're, of course, feeding it the name of the data set to be referencing here. So we're going to go ahead and build model A. And then we're going to take a look at the coefficients that are generated when we estimate model A using this LM, this linear model function. And what we hope to see at this point is we hope to see the same values that we got using that pseudo-inverse approach, so we can be confident about what is going on under the hood when we are applying that LM function in R. So let's go ahead and report the model A coefficients. Okay, and you can see here we have some similar values. In fact, we have the same values. Here is our intercept from the pseudo-inverse approach. Here is the intercept using the LM function. They are exactly the same. And you should be able to go through and verify that this is also the same for every other one of the variable coefficient estimates that we've generated. Cylinders there, same value here, so on and so forth. Number of carburetors, there's the effect of that, it's negative 1.994. Right, we see that same value here. So we should be comfortable at this point of how we construct that X matrix, how we construct the Y vector, how we create the pseudo-inverse matrix by taking the X transpose X inverse and multiplying that by X transpose. And that pretty much wraps up our verification of applying that pseudo-inverse technique in R specifically. Hope you enjoyed. Stay tuned for more. Have a good one.